Okay, so thank you for joining. I'm just presenting an outline now of the presentation. So we're going to have some introductory slides that talk about what the oversized cavity theory is. You may have heard it as the power balance method before. And then we're going to do a demonstration of this powerful and efficient technique using this ADF Galileo software tool. There will be four brief videos that are going to be presented that I will be talking through. One is going to introduce the platform and the satellite and just kind of give an introduction to the software a little bit. And then we'll perform a basic OCT simulation on this satellite. And then we'll start to add some complexities. We will add a victim to a cavity. We'll add an absorber. We'll look at how the frequency can be changed of the frequency range of interest. And then we'll present a final one where we add an emitter as well to the cavity. So the basic context for this webinar, or for this OCT, Oversized Cavity Theory, is looking at analysis at high frequencies. In this particular case, we were thinking of radiated susceptibilities, but you could also imagine this being a problem for high-intensity radiated fields as well. Kind of in our minds, at EMA, the cutoff here is about 2 gigahertz for the analysis. So at frequencies below 2 gigahertz, we recommend a full wave analysis, and at frequencies higher than 2 gigahertz for this type problem, we recommend the oversized cavity theory or power balance method. The full wave solver, full wave means it's a full solution, full numerical solution for Maxwell's equations. This is obviously the ideal way to approach the problem, but for instance, as the mesh decreases, to get to high frequencies, you have to have a smaller mesh size. So we have a bullet here. The simulation time for a time domain solver scales to the 4th power of the change in mesh size. So if you need to go, if you want to double your frequency range, you need to cut your mesh size in half, and that's 4 times more computational power to get there. And frequency domain is also limited by the mesh size. So the requirements might go up to 40 gigahertz in some cases, and this is also in the regime of OCT. The oversized cavity theory it provides a statistical description of penetrating fields. It's very computationally efficient. There's no mesh and there's no numerical solution into Maxwell's equations. Very broadly speaking, it's valid for a reverberant cavity. You can think intuitively of a cavity large relative to the wavelength of interest. We'll show an example during the demo where we find a regime where it's not valid. That's one of the nice things about this tool, is that it checks that validity. But there are more rigorous criteria that it's based on the statistical properties of the field and ensemble averages, and there's a whole host of rigorous criteria, but intuitively you can think of something large, hence we say oversized cavity. So some of the basics are that there's a pretty simple relation between the power density inside a cavity and the power density that impinges on the cavity, or the incident power density. It's related, it's sensitively related to different types of cross sections and this quality factor. So the quality factor, they're shown below in one of the bullets. There's a line with some equations that show how the quality factor, the quality factor describes how energy is absorbed or lost in the cavity. And there's cross sections on how For instance, the size of apertures, and you see one that's related to the conductivity of the walls, and if there's any absorbers as well. But assuming you can accurately describe the quality factor and the impinging field, then the internal field is straightforward to obtain, and so that's what we'll be taking advantage of today. So, as we discussed, we're going to be using the ADF Galileo software suite to do this analysis. This is a very powerful tool for EMC risk control, as we'll be seeing here today. So here's an example of how people use this tool and the oversized cavity theory to do a radiated susceptibility assessment. So for instance, the ESA has a satellite, the OHB satellite, and they have certain RS requirements, radiated susceptibility requirements, and they have a very complicated platform, as you can see in the slide here. Well, they need to evaluate the electromagnetic field in the internal cavities at 12 gigahertz. They have internal transmitters and external antennas. Now, the nice thing about the oversized cavity theory is we can take that complicated design, that complicated satellite platform, and reduce it down to a topological description of cavities and evaluate our susceptibility. So why do they not use the full wave solver to do this problem? Well, as we mentioned, it's not practical. The simulation involved would be very difficult to do a full wave solution, but it's also not useful. You can get essentially the same information in a much more efficient way using this approach that we'll present today. So as we said, it's efficient. You'll see directly in our demo, it only requires seconds to do this for our whole notional satellite, which we'll introduce in a minute. And kind of the structure here is that it is a topological description of the platform. You have a description involving cavities, and within each cavity you have panels, and then you may also have absorbers, emitters, and victims in the cavity, and then within the panels you have apertures, and then the apertures coupled to external sources. It's actually a very intuitive way to design the simulation, to set up the simulation geometry. And we'll see that as we go forward, but it's a pretty intuitive way to do a radiated susceptibility analysis in a very quick way. And that's what the GUI looks like that has that same structure. You can see you have the cavities, you have panels, you have, and then you have other items within that. Okay, so we're about to start the demo part of this. We're going to look at this notional satellite, and over the course of these 4 short videos, we're going to do a pretty thorough radiated susceptibility assessment for this notional satellite geometry. Okay, so now we start our demonstration. This first video, we're going to introduce the geometry, which is shown here. This represents a possible satellite geometry with cavities and antennas on it, apertures. You can see the nice list here. We'll look inside of one of the cavities. You can see all the apertures are shown, and they're outlined in blue there. So there's internal and external apertures for this satellite. And all of these cavities will be represented in our OCT models, so that we'll see explicitly how the cavities are called out. You can see we have an antenna here on top as well, which is highlighted. And eventually we'll add some internal emitter as well. So now what we can do is, we'll look over here. This is where the OCT geometry is actually explicitly laid out for us. So on the left side, we have this hierarchy of the model, and now in the middle here on this GUI, we have the geometry represented for our OCT simulation. So all the cavities are represented. You can see the 5 cavities here are labeled A, S, W, E bottom, C and W, and the volume specified. And that's about all it is to get started, to add cavities to the model and the volume associated with them. And now you can see that we have the panels associated with this cavity. So there's some external and internal panels associated with this particular cavity. And again, each one has some conductivity, it has some area, it's either internal or external. And there's a pretty straightforward, actually, the user interface is straightforward to understand and intuitive to build the model up. Now within the panel you have apertures. And so these apertures again are defined by the location and an area. There's also some modeling options available. So there's several. So pretty much each of these panels has some aperture in our model, and there's also sources. So then once you have an aperture, you have to specify the impinging source. In this case, we've specified plane wave sources impinging on the apertures. There's also an option to couple directly to the antennas, so you have that option as well. In this case, we've done a separate analysis to determine the impinging field on the satellite. Now this platform also easily allows you to add things within the cavity. So for instance, you can add, we haven't shown it yet, but you can add emitters and victims and absorbers very easily within this. For instance, we'll be adding in another demo in a minute here, but you can see with the right click on the A panel, you can add equipment which would have an RS requirement or a lossy object or internal probes, things like that. So it's very easy to add more things to the geometry just with simple clicks of the button. You could add a cavity as well. So that's kind of the outline for the introduction of our geometry and the introduction of how to set up the geometry and what we're looking at. So now we're going to go to the next demo where we're going to actually do our first OCT analysis on this geometry. Okay, so we look again here at the geometry, and now we're going to look at how to actually do the OCT analysis. So we come to the General Settings tab, and you can see we have a frequency scan specified. Now, we might have chosen this particular set of frequencies due to the antennas on our model, or what we think the source is that's appropriate for this model, what the impinging field will do. And so, for instance, on this particular model, some of our antennas, one of our important antennas is in this particular frequency range. And so that's why we've looked at it. It's easy to add other frequencies. A frequency scan we're showing now is pretty straightforward to create a new one based on whatever frequencies of interest the user has. So you can see, you can just simply add some to a list here. And then you can also pick a linear or logarithmic calculation of a set of points based on a min, max, and number of points. So maybe we picked something like 150 points between 1 gigahertz and 10 gigahertz in this case. And so that would be pretty straightforward for the user. But for our purposes, we'll stick with this particular scan, 7.5 gigahertz scan. All right, and so all we do is just click the button. We've already specified the geometry, and now we can look at the results. So what can easily be shown through the graphical interface is just plots of various things. So particularly we have the E field inside each cavity plotted over this frequency range, around 7.5 gigahertz. This is the mean value based on our statistical distribution. You can switch it over pretty easily to look at the E field distributed by cavity. So maybe you want to see more quickly which cavities are the problem cavities. You can also look at the number of modes excited within each cavity. This can be an important way to understand the applicability of the OCT. And then it also has the quality factor within each cavity. So you can get the quality factor out, and maybe you want to do some back-of-the-envelope calculations with the quality factor. So all of these things are helpful. And then, of course, you have the statistical data available, so we can switch from the mean value to certain percentiles, 90 or 97.5 percentile in terms of the confidence level of the intensity of the field. So the 97.5 is the highest field, and that might be the one you want to design against so that you can have confidence going into your test. There's also a standard deviation which shows sort of the spread of the statistical distribution of fields. Now, there's also a way you can look at the text file output from the simulation. And this is, in some ways, this is where most of the data is, or the most thorough description of the simulation comes out. You can see it tells us some summary information about our different frequencies. You can see here the first section covers the 7.3 gigahertz scan. That was the first frequency in our scan. And then we'll spend some time looking at this first cavity, ASW, one of the cavities, one of the 5 cavities. So it tells us, already it tells us like the mean electric field, standard deviation. It tells us things that were part of that plot we just looked at. It has the power density as well. Has some information such here as the quality factors broken down between leakage and walls. You can see there's also an information about the excited modes available. Now there's no victim in this cavity yet, so there's nothing to report on in the susceptibility report, but we'll look at the next demo. We'll see when we add a victim how there's you'll get a full susceptibility report related to each victim, and it will discuss the applicability of OCT and things like that. You can see then you could scroll down to the next cavity here, very quickly get results out, and this becomes very useful once you have the victims present, because then you can very quickly look for the immunity and susceptibility to the for the victims within each particular cavity, and that's very useful. Okay, so that's the end of our second demo, or the second video of our demo. Now we're going to go and actually look at adding a victim here. We're going to look at different frequencies, and we're going to add an absorber as well. So you can see that it's pretty easy to add something. It's called an equipment normative. So here we're adding what we just call it RS victim. It's going in cavity A. We're going to specify some bandwidth for it and some threshold electric field. You can see we have a few options here, power or electric field and other things. We're going to go with the electric field in the cavity, and we specify some threshold. We're going to run our OCT again. It's the same thing we just did, but now we've simply added a victim into one of the cavities. Okay, so when we look down here, we have all the same information, but we have some new stuff as well. So we have the same, Q analysis, the same internal field analysis, but now we have a susceptibility report. So what does this tell us? Well, what we can look at here is that we see the margin for our victim is negative. That means that we're coming in, the fields in the cavity are exceeding our threshold limit according to the simulation. So that's what the negative margin means. Another thing it tells you is that it gives you an assessment of the OCT applicability. It tells you the number of standing modes, 153, and I believe the threshold is 60 for this simulation. So it means that we have confidence in the OCT theory or the OCT approach for this problem, but it also gives you an immunity probability for that victim. So you can see we've got about a 13 or 14% chance of passing a test or being immune to that environment based on this simulation. So you sort of get a sense of that with the negative margin, but you can see that we're probably not in a good state for this particular design and that particular victim, the way it's set up. But now let's see, we could modify our design a little bit. Let's add a lossy object in the cavity. So we're going to put in an absorbing object. We'll pick some volume within the cavity. And then we have to pick the cross-section as well for this particular object. And then we just rerun. We just changed our geometry that quickly. And now we're going to, first let's look at the display. So you can already see that in this A cavity, the field levels are much lower. So that's a good sign. A is in the blue. Actually, the other field values are also lower. Recall that these cavities are interconnected, so all of the cavities get affected by the one cavity as there's an absorption. If we take it to the 97.5 percentile, it's a little higher. So let's have a look at our susceptibility report now. So now we come down and we see that for this victim, adding this lossy object to the cavity has helped. So we're still in the OCT applicability, but you can see that our interference margin is much closer now. So we're actually in the positive margin with respect to the mean value, and just negative with respect to 97.5 percentile. And we calculate from that, or we ascertain from that the immunity probability is now up to 99.8%. So a much better situation. Maybe not entirely perfect. Maybe you want to get it with some positive margin, even at 97.5 percentile. But you know you're on the way. You know you're moving in the right direction with that. So that's kind of one of the utilities here is you see the applicability and you see the margin for each victim in a very quick way, and it's very efficient and very useful information like that. So now let's delete the lossy object and we'll pick a different frequency scan. So we have a 2 gigahertz scan, so it's a lower frequency. So this will be around 2.2 gigahertz. As you can see in the list there. So we deleted the lossy object. All we've done is change the frequency range here to a lower frequency. Now let's come down and look at our report again. First, we'll look at the display. You can see that the results have changed to this region around 2.2 gigahertz. And you have, again, the field distribution in the cavities. So the same set of machinery available. Now, if you scroll down, what's interesting is that you have all the same information we've had before, but now when we look at the RS victim report, you can see that we're not in the region of OCT applicability anymore. So we've gone to a lower frequency, and we haven't been able to excite as many standing modes. And so the software is telling us that this may not be reliable. You may not be in a reliable regime. And it also tells you here that assuming, even if you ignored that and assumed we were reliable, you can see that now that we've removed this lossy object, we're going back into an area where we don't appear to have good immunity. So not that we can trust this result, but it would say we're back down to around 11% chance of immunity for this setup. And for this particular problem, that's kind of what we would expect, because the geometry is not so complicated that we would expect the frequency change to necessarily to change our immunity when we have such a simple cavity. Okay, we're going to look at one more. We're going to look at one more video. The last one's a short one here, where we're going to add an emitter to this problem. So we'll stick with the same setup. We have again, we're looking at the 2200 megahertz scan, 2.2 gigahertz. What we're going to do is we're going to add now the lossy object back in there, just to see. Hopefully we'll see that we find that our victim is now has immunity again. So we'll put a lossy object back in, rerun this analysis, and we'll look at our results. And so as you probably expected, we find two nice things here. The first one is that we find applicability now of the OCT theory. So putting the lossy object in there helps excite more standing modes, and we find that we are in the regime of the OCT. And we find that we have good margin, particularly with respect to the mean value. We have nice margin. We're a little below at 97.5 percentile, but the immunity probability is back up to 1. So that's good. We've added the lossy object. We like our design, and we find that's good. Now we're going to add an emitter. So we'll add another equipment nominative. We'll call this one emitter within the cavity. So it reruns with the emitter. You can see, looking at the display, the results have popped back up for this cavity, particularly at that 97.5 percentile. They seem to be like we might be above our threshold again. And we'll come back down to the results here, and what we can see again is that yes, we are in the regime of applicability for this approach. But our immunity probability is much lower again, down to 15.6%. And that's to be expected. We've added an emitter within the cavity. It was just on the threshold before, and now we're adding more energy into the cavity. And so, and now you can see, though, about how you can analyze your design so quickly. And so, as our conclusion slide, we've tried to show that this power balance method, OCT, provides an efficient way to assess the vulnerabilities at high frequency. We used the ADF Galileo platform to do this analysis on a notional satellite. We added a lossy object, we added a victim, we added an emitter. We showed how you could, within the course even of a day probably, design and check at least at a basic level the susceptibility of a platform and have some pretty good confidence level of where a design stands in a pretty quick amount of time. So thank you for joining our webinar on Oversized Cavity Theory, and we might have time for a few questions. So bear with us for just a moment. Okay, so so ADF is a software tool that it originates with this company on the upper left part of our screen here on the slide, IDS, an Italian-based company. We have partnered with them, so we've become a formal partner with IDS, and we are their exclusive distributor for ADF in the United States. So it's part of the EMA. Company now as far as being a distributor and user of that product. It's not EMA 3D, but it is part of what we have now. It's part of what we're offering as a software tool, and it's part of what we use for analysis. So that's a good question. We didn't spend much time introducing that. The software itself, ADF, is going to be re-released as Galileo pretty soon, but it's the same tool you saw today. It's just a name change and maybe some change to the broader package. Okay, we'll leave time for a couple more questions here. And if you have questions and you didn't think of them at this time, or you didn't want to submit them to the chat, you can always follow up with email. We have our email address listed here at the bottom, bryon@ema3d.com. And any questions that we didn't get to today, we'll follow up with emails from. So I guess at this time, that's all the questions we have. Thank you for your attention. Thank you for joining. Please follow up with us as you're interested. I think anyone who joined will get a follow-up personalized email from Niels, and we hope that you might have some interest for further discussion with us. So thank you again for your time.